ghost woman was spotted on Mars not too long ago from some of the Mars photographs that we have coming from our satellites and explorer vehicles that we have there. As you can see here, there's this very strange looking image here, and then when you blow it up, it looks kind of like a ghost woman of some kind. I also bet you didn't know that there's a rock head of President Obama on Mars. You see, and then also, of course, we know about the very famous face on Mars, right? And supposedly these are pyramids, right, that were built around the face on Mars. So, are these things real? Are we actually seeing are we actually seeing these real objects, or rather is it some kind of illusion, right? Probably the latter. It's probably an illusion, and it's probably due to the fact that we perceive things in very strange ways sometimes. Our perception of objects is a very complex issue that we're going to get into in this chapter, chapter 5, perceiving objects and scenes. So one of the problems we have with perceiving objects and scenes is that the stimulus on the receptors, in other words, the light that falls on each of the receptors is very ambiguous if you think about it. The image on a retina, whatever's projected on a retina, can be caused by so many different things, right? For example, if I were to say have this object here, right? If I were to have this object here, and this sends a rectangular image to your retina, right? This would also send a very similar image as with this. I'm tilting it back and forth, right? But really, it's really hard to tell just from the flat image that's being transmitted to your retina what exactly is going on. Objects can be hidden, right? This notepad doesn't become half a notepad when I do that, right? Yet we still perceive it as a whole notepad, and we actually day to day go through our whole ability of recognizing objects that are only half there or blurred. Take this cityscape shot, for example. We recognize these things as buildings having a particular shape. But if you think about it, there are all these different weird shaped blotches and different different trapezoids and rectangles and different shadows, and parts of the buildings are hidden, yet we still perceive them as whole buildings, right? So if we look at this image here, right? So here's, building A, which is in the shadows, right? Half of building D is being hidden by A, yet we know that it continues on through there. Buildings B and C, are they two separate buildings or one separate building, right? All of these ambiguous things land as flat images on our retina, right? And it's up to us, it's up to the perceptual mechanisms of our brains and of our minds to be able to untangle these flat images and turn them into three-dimensional perceptions, three-dimensional objects that we recognize, right? Faces are a very classic problem, right? What's the difference between, say, this face and this face, right? Is this face and this face the same person? Are they the same person? Now, our brains know, right? Our brains know that these are two different people, right? But when you get right down to it, trying to determine what exactly is different between this person and this person, and how it is we recognize it very quickly, is a very difficult thing to do. Another really difficult thing to do is to match this face with this face. In other words, machines, it's very difficult to program machines to be able to do this task where they recognize this face very easily, but they don't recognize that this is the same person. That's a very, very difficult thing to train machines to do, because we have not been able to represent in machines this thing as a whole object that can be rotated in space. Um, there was several years ago in London, they tried to develop a terrorist detection tool. If you've ever been in London, you'll know that it's covered with cameras. There's cameras everywhere in London. So somebody got the bright idea of coming up with this automatic computer analysis tool that would look at faces in crowds going by all the cameras in the city and be able to detect possible terrorists walking around in the crowds. And it turns out this system identified 90% plus of the people walking around as possible terrorists, right? It's just a very difficult thing for machines to do. Here is a machine that is designed to look for windows and look for walls, right? Detect the edges of walls and the edges of windows. This might be really useful, say, if you're a architect or a home decorator and you can bring the camera in to take pictures of a place and then have, from those pictures, have a three-dimensional model built, right? That would be really cool, but it's really hard to do, right? For example, on this side here, we have the machine did a pretty good job of recognizing the walls, right, and the edges, but it really didn't pick out the windows at all. Whereas here, this machine seems to have done an okay job picking out the edges of the walls and the ceiling, but it called this a window. It called this a window, and it put something here. I don't know what this is, but it put something there, right? Building a machine that can perceive objects is really, really tough. It's a task that we have not mastered yet. I can tell you, as somebody who works in the artificial intelligence field, I can tell you that it's a problem that we have not figured out yet. One of the big challenges we have, for example, is to build machines that can look at X-rays, MRIs, and help doctors to diagnose diseases and other conditions. There's certain, like, for example, looking at lungs, right? Looking at a chest X-ray. A trained radiologist can look at a chest X-ray and within 2 seconds, know what's going on in that X-ray. You know, if there's nothing there, if there's something there. We can't do that with machines, right? It's just a very difficult problem. The stimulus on that flat surface is just an ambiguous blotch of lights. That image can be caused by anything. Plus the objects can be hidden or blurred, right? So for example, and this goes back to the example I showed you earlier, right? If you look at a flat page, it's projecting a certain image on the retina. But I can make that flat page, right? I can angle it, and I will know that I'm angling it, right? I'll know it's being angled. But how do I know that? Because the image on the retina is almost identical, right? So it's a difficult problem, how we relate our perception of movement and our perception of things that are missing. How we're able to extract that information from very ambiguous sorts of images that are being projected onto the backs of our eyes, right? We look for patterns in, where we are, where we're looking, right? One of the things about our detection mechanisms is that we create patterns, right? And the way the patterns that we create and we detect depend heavily on our perspective, where we're at. So if you look at these, this looks like a nice stone circle, right? But it's not really a circle. It's only it's only seen as a circle from a certain balcony of a certain building. When you look at the actual arrangement of the stones, it looks like this, right? It's a lot like those chalk drawings that you see, those big giant chalk drawings that you see artists do, that where if you stand in a certain spot and it looks like this beautiful three-dimensional image that's on the ground, but when you look at it from another angle, you can tell how it's been skewed to look three-dimensional, right? So like I said, objects can be hidden or blurred. Now, look at this image. Look at this image, and I'm going to give you 5 seconds to find the glasses. Find the glasses in this image. 1, 2, 3, 4, 5. You probably already found them, right? The glasses are right here, right? Now, we are very easily able to do that, right? Find the book. Here's another one. Find the book, right? And pretty quickly you see that there's a book there, right? You know that. Even though the book's obscured, even though the glasses, there's only this little piece here, actually, of the glasses, right? In spite of that, in spite of this very limited amount of information, this little blotch just being painted onto your retina right now as you look at it, we're able to know that those are glasses and that's a book, right? Again, you don't really appreciate this ability that you have until you've tried to program a machine to do this. Machines cannot do this. It's very, very difficult for them, right? Here's another example. Identify these faces, right? Some of you may be a little too young to recognize some of these people, right? But looking from left to right, that's Prince Charles. This is Woody Allen. This is former President Clinton. This is Saddam Hussein. This is former President Nixon. And this is Princess Diana, right? Now, my brain didn't have that much trouble telling who these were, right? And they're blurred images that a machine would have a very difficult time reading, okay? One of the big challenges is viewpoint invariance. That is the fact that knowing what an object looks like, no matter what angle you're looking at it from, right? So, you can take your cell phone, right? And we know that's a cell phone, right? We're pretty good at saying that's a cell phone too, but is that a cell phone? Right? Is that a cell phone? Is that a cell phone? Our brains can look at that and say, yeah, that looks like, that's probably a cell phone, right? Could be a tablet, but it's probably a cell phone. A computer would have a very difficult time with that, right? Knowing that that's actually the same object that we were looking at before, right? Here's another example, right? A chair, right? You'd be surprised how tough it is for computers to do this. Now, there have been quite a lot of advances made. Google, as a matter of fact, actually has a pretty good vision identification system. It's an automated system that can identify objects in pictures. And they use it for classifying, right? So Google, of course, has everything that's on the internet, and they actually have an AI now that goes out and classifies pictures and can look for very fine details in pictures, for example, with different products. And when you use the Google Shopping feature that has pictures of all the things that you're shopping for, this software is able to pick the exact right picture for the thing that you're looking at. The Google device, the Google AI would probably not have too much trouble with this one, but that Google AI is a massively complex system, huge. It's a massive neural network. I heard a talk a couple of years ago, from the lead research scientist from Google, one of the many PhDs working on that AI, and he said that Google no longer knows how that AI works. They don't understand how it works anymore because it's gotten so complex. That project came about a few years ago when Google built an AI that was trained to find pictures of cute cats on the internet, which I think is kind of cute. Looking for pictures of cute cats, and this thing had better than 95% accuracy in finding pictures of cute cats on the internet. And from there, it's grown into this much more complex AI that can do this task, but it's still a formidable task for most machines, and it's something that we can do quite easily, right?